Integration by parts. This is section 7.3. Okay, sorry, all the sounds you hear are because I just let my dogs in, and it's like a giant dog rodeo in here. Integration by parts. This is a very common integration method. It's used in a lot of different math classes, not just Calc 2. So it's something really common, something you're going to want to focus on. So the reason it's necessary is if you have a problem and regular u substitution won't work, like this problem right here. So if I had x times e to the negative x dx, I couldn't use a regular u substitution method. And the reason I couldn't is, let's say you decided to try to make e equal to u, and you said, oh, okay, so u equals e to the negative x, and then du, well, that would be e to the negative x divided by times negative 1, sorry, which would be negative e to the negative x dx. But if I tried to do u substitution, there's no way I can tell what x is supposed to do. So I wouldn't know how to substitute in there. So that's when another method is needed, and that method is called integration by parts. There's a pretty cool formula that this comes from. There's a proof of it in your book. It really comes from that original limit law where all your derivatives come from. But the formula says this. If you break this expression into two pieces, and you call one of them u and one of them the derivative of v, so notice I have two different variables here, a u and a v, then that is equal to, by this property, u times the original function v minus the integral of the original function v du. So that whole thing right there, and then you would evaluate the antiderivative of v du, and you would get your final answer for the integral that you started with. So that's the whole theorem principle behind integration by parts. And you always, by the way, it doesn't matter who's teaching this class or where they're teaching it, they always use u and v for the notation, so that's something you're going to see regardless of where you use this. So, oh wait, let's go back up here. All right, so I'm going to talk about how to use that with our example here. Your job is to pick what parts out of your original expression, what part is going to be u and what part is going to be dv. Now, the dx portion, by the way, always has to be part of dv because it is a derivative, and that's what it means, the derivative of x. But then you have a choice of where these other two go. So you have an x and you have e to the negative x. Some of these problems, there's no real trick to figuring out which is which, and you may get it wrong, and you'll know you get it wrong when you start to try to solve the problem, and you realize when you get there, you might end up with a worse expression than you started with. But one trick is, generally speaking, if you have an e expression as one of your function values, as one thing in your integral, that's usually what you're going to want to reserve for your dv. So I'm going to do that here. I'm going to make the e to the negative x dx my dv, and that makes the x part of my u. Okay, so I have accounted for the x, the e to the negative x, and the dx in my original integral. So I have u and I have dv. Now, according to the formula, I need to figure out what the original v expression was, and I need to know what du is equal to. So we're going to go ahead and find it. Du. What's the derivative of u? Well, if u equals x, the derivative of x is 1 dx. So du is equal to dx. So I have that one. Now, if I know the derivative of v to get back to v, well, that's what the integral symbol does. So antiderivative of e to the negative x is e to the negative x. And you always divide by the derivative of the exponent, which is negative 1. So v is equal to negative e to the negative x. Now we're going to apply the formula. Formula says u times v. So here's u, and here's v. So put them together, and I get x times e to the negative x. And I do have that negative in front, so it's just going to go in front of my whole expression. So I have negative 1, or negative x e to the negative x, minus, then we have our little integrand, v, which is negative e to the negative x, times du. Du is equal to dx. So I have that expression. Now I have to solve this. I need to know, I have to do this little integral here. Now that negative in front of my e, it's a negative 1, it's a coefficient, so I'm going to bring that out. Negative x e to the negative x, that would make it plus, once I bring that negative out. E to the negative x dx. Okay, that's just a regular old integrand. I can do that one, not a problem. Negative x e to the negative x, antiderivative, e to the negative x divided by negative 1. So I have negative x e to the negative x minus e to the negative x. There are no definite values to plug in, so that's why we have to do our plus c, and this is a perfectly fine answer. Sometimes in this section, when you're checking your answers in the back of the book, if there's something that can be factored out, like I could take out a negative e to the negative x out of both of those, and that would leave me with positive x plus 1. Sometimes your book will do that, so if you're checking your answers in the back and it doesn't look like yours, just look to see, did they maybe factor something out. But this one is fine for me, it's fine for our purposes here. All right, so that's example 1.